Okay.
So the last talk in this session.
Sure.
Okay. The last talk will be on linear sea breeze model relevant for the tropical regions.
Oh yeah, you need this one. This invitation. So the title of my talk is that linear sea breeze model. This is done jointly with the PhD student Arnab Gupta and Ravi and C.V. Sriniwas from the Indira Gandhi Center for Atomic Research. Okay, so what we are interested is in the flow field around Kalpakkam. Kalpakkam is a coastal site located between Chennai and Pondicherry. More is somewhere here. This is Chennai and this is Pondicherry, somewhere there. So that site holds a lot of nuclear facilities and an upcoming fast breeder reactor there. So the need for wind field simulation along that with measurements is obvious. And so IGCAR proposed a round robin exercise for atmospheric flow field modeling. And the task proposed by us was to implement a Kalman filter on a linear sea breeze model. We have not been able to implement a Kalman filter, but at least we got a linear sea breeze model going. So we looked for the reason for looking for a linear sea breeze was because, as Amit pointed out, nonlinearity does not do well with Kalman filter, and also this question of finding the adjoint. Should one discretize the adjoint or take the adjoint of the discrete? So we wanted to minimize that. So thought we'll look for a linear model. And however, we could not find one that incorporated both the Coriolis and non-zero. So we decided to combine a couple of references, those two references, where some linear theory was done. And yes. So let me just say how it was. Okay, here is a plot of sea breeze occurring at various heights, 4.8 meters to 78 meters. And this was done at Karachi, and the measurements were taken by Ramdas. So he was there in Karachi making measurements of the sea. 31, yes. So, yeah. And the reason why linear this sea breeze is more relevant in tropics rather than the mid latitudes is clear from this table. If you see the mean number of days with sea breezes in Bombay and in near Kerala, near Trivandrum, Karachi, and Madras, the number of this is quite large compared to mid-latitude regions. So this is from the book of Atkinson. So definitely it is a tropical. So here is a typical schematic of a mature sea breeze. It gets heated up at the land and then has a circulation in that fashion. Okay, and here's a satellite picture. It's not so good. Perhaps the first satellite picture of the subcontinent. So you can see that this part near the west coast is completely cloud-free because the sea breeze is setting. And here is our reference frame. So our coastline is located along the y-axis, and we assume no variation along the y-axis, only in the xz plane. So linearize around 0 and consider the perturbations. So the important thing here is that there is a Coriolis force F V star and F U star, and hydrostatic, and heating is considered in this fashion. It's a diabatic heating profile with the scale height of h and length L, and Q0 is the flux. Yeah, Kian, they do not have the second component, and this is how their equation looks like without the Coriolis. Okay. On the other hand, Rotuno will have these F and V. Sorry, no V, only F. And so that is why we decided to have both together. Now just a small digression to tell you the hazards of neglecting a horizontal component. This was decided while doing the Nimitli project. And so we took a very simple system which looks like this. No gradients in space for u, v and w, but both the Coriolis components. I just want to show you what happens if you neglect FH. It's not obvious from this system, but however if you...
I'm puzzled. FH by scale analysis is very weak. FH is tiny.
Okay, but if you make it 0, there's some problems.
It's a singular limit is what you're
Okay,
saying.
yes. Yeah.
Okay.
Yes, yeah. No. This is just a simple system to show if you were to put FH equal to 0, how the solution looks like for a linear system. But, yeah. But,
Unless you're on scales of less than 10 kilometers, the horizontal Coriolis is tiny.
okay.
Keep
So,
that in mind.
sure.
So it could be a singular perturbation parameter. I don't.
Okay. All I want to show is that if you were to consider a solution like this, and if you, yes. Yeah, this is a special system, just to show a mathematical degeneracy. If you were to assume fh equal to be equal to 0. So by considering this special answer, no, this is not the final problem. This is just a small digression, as I mentioned there. So I just want to show how the exponential. So ultimately, you will get a system like ODE like that, and if you calculate the exponential, what you have is here fh, fh, and fh, and if you set it equal to 0, you lose the time dependence. That's all I want to say. It's not obvious. Yes, yeah. What I'm saying is not obvious by looking at that matrix or by looking at that system. On the other hand, when you calculate the exponential, you see that when fh is 0, your solution is given by e to the minus ta w0, and lambda naught are the eigenvalues. So if you were to calculate this guy, the last component loses time dependence. That's all I want.
The last component is what? Velocity?
For a vertical velocity.
Vertical velocity.
Yes. Yeah. So it remains at.
So what happens to the solution is not going to differ. If you took the FH into account.
Yeah, then these terms will remain. Sine square root of lambda naught t and cos.
So it's a Remy.
Yes.
It's a ray,
Yeah.
which is missing if you didn't have
Yes.
rubber.
So in other words, vertical velocity remains at the initial value for all time.
Can you say what lambda naught is?
There.
Oh, sorry. There.
Yes. Okay. So now we go back to the original system, make all this non-dimensionalization, and this is the system.
Oh, you have to use non-hydrostatic equation.
Okay. In that W, you mean?
Yeah.
This one.
Here's the problem. If you're arguing the vertical Coriolis is important,
Yes.
when you do a scale analysis, it's only important on scales less than 10 kilometers.
No, I'm saying horizontal component.
No, the horizontal component
Yes.
of Coriolis is only important on scales of less than 10 kilometers. And on scales of less than 10 kilometers, if the atmosphere is more than 10 kilometers deep, it's where non-hydrostatic effects also
Okay.
play a role. So you can't use the hydrostatic equation.
Yeah. You mean instead of 0, there should be a G
Yeah,
here?
you should have buoyancy.
Yeah.
Buoyancy effect.
Yeah. Okay.
So you've mixed two different things.
Yes. No, but even if you had a gravity here, it is not going to affect the exponential of the matrix.
No, but it's a coupling.
Yeah, that's right.
And it gives you the time dependency law.
Right.
So you mix hydrostatic and adding a term that is only important when non-hydrostatic.
Right. No, it's just a mathematical curiosity. But it's dramatic that it loses time dependence in this case. Okay. So, yeah, so after non-dimensionalizing, we get this system. And then we eliminate, use the stream function, and then write it as one equation in terms of stream function. So this is the system you would get. Yes. So what's important is the gradient of the heating there for the stream function. Okay. So now in case of Rotuno, you would get the last equation, namely because he didn't have this u equal to 0, so he gets only f square minus omega square. Whereas what we get is the equation 21, and the difference is that this changes sign, and so it becomes from elliptic to hyperbolic. So that's what Rotuno's analysis. I borrowed this from Robert Fowell's homepage. So here the notation is slightly different, but we can see the behavior, namely when f square minus omega square changes sign, it becomes from elliptic to hyperbolic. And so what he says is when it is elliptic, you have some interpretation, namely the sea breeze circulation is spatially confined, and the circulation in phase is with the heating, and the amplitude decreases poleward. And if it is hyperbolic, then you have it's extensive. Of course, now it is a propagation, and the onshore flow is strongest at sunset and strongest at midnight. And when the term vanishes, there's some singular equation is single. Okay, so now we also do a similar analytic solution. Take the Fourier transform, and then you are able to write the psi in terms of these four integrals. Okay, so the stream function is given in terms of where b is that v of psi. Let me go back and show what this capital V is again. Yes, V is U by NH. Okay, so we write this as sum of four terms, and we are interested whether these remain bounded or not, especially because the denominator can vanish. So one can show the first integral is bounded in that fashion. Just pull that out, and then you get it's bounded by 2L e to the minus z minus 1. We made an extensive analysis by looking at, even though the denominator vanishes, the integral remains finite. And for psi 2 and psi 3, the integrals are in the finite domain. And for the two infinite integrals, we are able to show this estimate in a quite straightforward fashion. Both are bounded by 2L e to the minus z plus 1. So in other words, the stream function here is well defined, and it remains bounded. So we can make an analysis. So similarly, U is writing in terms of stream function. You get U and also W again in terms of these integrals. So now these are hard to evaluate, but then use Mathematica and did a cutoff for this. You can't do infinite integrals, so we made a cutoff for the infinite thing, and made sure that if you varied the top, the integrals did not vary much. Okay, so here's a plot of the solutions as a function of latitude. So what I have here is the horizontal velocity for 10 degree north with those parameters for capital V of this, and for 15 degrees and 25 degrees. So these oscillations are purely numerical, it's not physical. So they vanish once you push the limit up. So, and then here further plots, again for various latitudes, and of course I will refrain from making any interpretation of these results. So as you move away from the equator, the it seems to show some pattern like that. Okay, so now what we want to do is compare it with some measurements. So here is a plot, and most of the measurements were made in Anupuram. And I think Tara made also a lot of measurements, so she's here. And perhaps this Anupuram data only is reliable. So here's a river streaming into the sea. And here's the first plot comparison. So at 50-meter level on 14th and 15th. So starting at 2 and ending at half an hour later. And then here is another. So although the comparison doesn't look all that impressive, what the person from IG car said was at least it is predicting the timing of the maximum and minimum value of the wind. Although here it is. Okay, so now these people have also calculated using MM5. So they also used MM5 and made a comparison. As I mentioned there, this was using some mini soda, Tara and her group, and Srinivas and Venkateshan and those people made MM5 simulations. And their conclusion was the following. Their comparison is like this. This is from MM5. So for instance, here's the wind speed at 9 o'clock in the morning, and then also at 12 o'clock, and then at 4 o'clock. So it seems the agreement seems to be good with MM5 at 4 o'clock and afterwards. It's not so good at 12. So maybe you can say why this is so. Okay. Oh. Yeah, incorporated in MM5? Oh, WR. Okay. So again, here is another comparison. So again, after 10, that seems to be okay, and okay. So one more, and this from the same tower in Anupuram. I chose those things which is wind measurements at Anupuram. Okay. So the assimilation of their conclusion from this is taken from their paper, that it did not improve the initial conditions greatly as they had a single point observation. And so to resolve this, they say that they have planned some network of automatic weather stations at these places. And so these hopefully will give a better initial condition. So
Network is there now.
okay. Okay. So I don't know whether they have made recent comparison with all those data. Okay. So our final proposal is that we set up a Kalman filter module, but then that is not yet ready. So the idea is to have an independent model other than MM5 and WRF, which will simulate the wind field around Kalpaka. So we have some thing, but again, it's not. This is a very special initial condition, special solution which we have considered. The initial condition is not yet in place here, and of course the agreement with the observations will not be good because this Q is not realistic, or at least gotten from the site. Yeah, it's somewhere here. Yes, this Q which we have, the heating profile, it does not correspond to the site location. So this is just an idealized Q, just picked out. So we need to get a Q which is related to this, plus initial condition. We have not solved this as an initial value problem, but as a special ansatz like this.
For data assimilation, that's one of the hardest problems to get the CD ready.
To get, okay. Yes. So you mean instead of the Q here, oh, I'm sorry, I'm going the wrong way. Yeah, instead of Q in the buoyancy thing, you must have it at the... Yes, yes. Yeah. Okay. Yes, so yeah. In that case, we may have a better heating. Okay, I think that's it.
There is actually...
Yeah, this is two-dimensional.
Okay, I mean, excuse me.
One dimension.
There is a very nice model with a higher order closure developed by Leif Enger. I can tell you later about it, which really does great job in doing sea breeze or land sea circulation.
Right. If not, we can do an announcement. Thank you very much.
So it's been an exciting week, and the person who did the most work this week was Ahmed Abdi, and we should really thank him very much for all the work he's done to make such a great meeting. And can you please bring them in? Equally. Oh, Robbie. Let's thank Robbie. Also, can we bring the staff in so we thank the staff? I'm sorry, Robbie.
He did most of the work.
Okay.
Well, as Andy said, I think all of us will agree that this has been a very exciting and illuminating week. And I certainly have learned a great deal during the last 5 days that I think I had learned in several years before. So on behalf of ICTS, I want to thank all the people who came here from India, from within the country, as well as those of you who came from far away. And when we started thinking about this program, we had in our mind a discussion that actually has exceeded our expectations. And I think I therefore want to say a very grateful thank you to all of you who come from everywhere. And for Andy, who as a member of the International Scientific Committee helped put together the right people, and other colleagues on that committee, and in ICTS, and Dr. Spenta Wadia, the director, who always supported this program very enthusiastically. So, thanks everywhere around, and most of all to you.